In the deepest pocket of space, James Webb caught 2/3 of all spiral galaxies spinning the same direction, a pattern that should not exist, a signal that quietly breaks one of the oldest rules in cosmology. Tonight, you will meet galaxies older than the universe itself, red dots hiding monsters inside them, and a theory so strange it places us inside a black hole. If you enjoy journeys through the impossible, tap like and subscribe so the next one finds you. Now settle in. We begin. The morning the picture arrived, scientists at the control center in Baltimore were not ready for what they saw. James Webb had only been parked at its observation point for a few months. Engineers were still calibrating mirrors. Yet the very first deep field image returned something nobody had prepared a press release for. Galaxies. Hundreds of them. Sharp, glowing, far too detailed for objects that ancient, and several of them sitting in places where the textbooks said nothing should be. Webb is not a small instrument. The telescope sits about 1 million miles from Earth, 4 times farther than the Moon. Its golden mirror stretches nearly 21 feet across, almost the width of a tennis court doubles lane. It catches infrared light, the kind of light older than our planet, older than our sun, older than almost everything you can imagine. When that light reaches the mirror, it has been traveling for more than 13 billion years. It is the closest thing we have to a time machine. The team had pointed the telescope at a tiny patch of sky, a region so small you could cover it with a grain of sand held at arm's length. They expected a few faint smudges, maybe some early galaxy candidates. They got something else. Bright objects, mature galaxies, structures that looked like fully formed cities of stars, sitting at distances that placed them only a few 100 million years after the Big Bang. That was the first crack, because in the standard story of the cosmos, the early universe was supposed to be quiet, slow, a place where matter was still gathering, still cooling, still figuring out how to make stars. The first galaxies were supposed to be small, faint, scattered. The first image broke that picture in a single afternoon. A senior astronomer leaned toward his screen and said something quiet. He said the galaxies looked too old, they looked too organized, they looked too heavy, and he was right. Within weeks, papers started appearing, then more papers, then arguments. Some of those early galaxies seemed to weigh as much as 10 billion suns. Some looked even bigger than the Milky Way, our own home, which had taken roughly 13 billion years to grow into its current shape. These distant ones had supposedly done it in 500 million. It was as if you opened a photo album, found a picture of a newborn baby, and the baby was already wearing a suit and holding a briefcase. Researchers called this period Cosmic Dawn. The first stars were supposed to flicker on slowly, gathering into clusters, then galaxies, then larger structures. Webb showed something faster, something denser, something that did not match the math. A few of the early voices tried to stay calm. Maybe the distance estimates were off. Maybe the brightness was a trick of dust. Maybe the masses had been overestimated. Reasonable explanations, careful science. And yet, every time a new image arrived, the problem deepened. More bright early galaxies, more heavy early galaxies, more objects in places where the standard model had whispered, "You will find nothing here." A pattern was forming, not in the galaxies themselves, but in our reaction to them. Each new picture pulled us further from the comfortable story. Each new measurement nudged the equations into territory they were never built for. And then someone noticed something even stranger. Not how old these galaxies looked, not how heavy they appeared. Something far harder to explain. The way they were spinning. The discovery began with a simple question. How massive can a galaxy be when the universe is still young? In the standard picture of cosmology, the answer is small, very small. Galaxies are supposed to grow the way a snowball rolls down a hill, gathering matter slowly, merging with neighbors, building over billions of years. The first ones should be faint, wispy, barely held together. That is what astronomers expected when they aimed Webb at the most distant patches of sky. What they found instead was a small group of galaxies that broke the rules in spectacular fashion. Mike Boylan Colkin, an associate professor of astronomy at the University of Texas at Austin, looked at 6 of them. 6 was a small number. 6 was also enough to shake the foundation. These objects sat at distances corresponding to a time only 500 to 700 million years after the Big Bang. The universe back then was a teenager, young, gangly, still finding its shape. And yet, each of these 6 galaxies appeared to weigh more than 10 billion times the mass of our Sunday. Some looked even larger than the Milky Way itself. The Milky Way needed roughly 13 billion years to assemble. These distant cousins had managed something similar in a tiny fraction of that time. Boylan Colchin said something almost quiet about the discovery. He said that if the masses were right, we were in uncharted territory. 3 words: uncharted territory. From a careful scientist, that is the equivalent of a flare gun fired into the night. The numbers were so strange that some researchers refused to believe them at first. Maybe the redshift estimates were wrong. Maybe the light was coming from something else mixed into the image. Maybe dust was hiding the truth. So follow-up observations began. More telescopes, more instruments, spectroscopy, which splits light into its colors and reveals chemical fingerprints. The kind of careful checking that takes years. Some of the candidates faded under closer examination. Others held their ground, and new ones kept appearing. Not just 6, dozens, then hundreds, depending on how you counted. A study from the University of Missouri pointed Webb at infrared images and found roughly 300 objects that looked far too bright for their supposed age. Candidate galaxies in the early universe, glowing harder than the math allowed. Imagine arriving at a maternity ward and finding most of the newborns already standing, walking, asking for car keys. That is roughly the scale of the surprise. The standard model of cosmology, sometimes called the lambda cold dark matter framework, predicts a slow build. Tiny ripples in the early universe pull matter together. Small structures merge into larger ones. Galaxies grow in stages over enormous stretches of time. Webb's images show something that bypasses much of that staircase, something that arrives at the top floor before the elevator has finished installing. Astronomers proposed every reasonable rescue. Maybe stars formed faster back then. Maybe the first generation of stars was unusually massive and bright. Maybe there was a hidden source of light we had not accounted for. Each fix solved part of the puzzle and broke another. The deeper the team dug, the clearer the pattern became. The early universe Webb was showing did not quite match the universe theory had built. That was strange enough on its own. Then came the second discovery, the one that did not just challenge the timeline. It questioned whether matter in the cosmos had been moving in a way nobody had predicted at all. To understand why those 6 early galaxies caused such alarm, you have to picture what the universe looked like when their light first set out for us. 500 million years after the Big Bang, the cosmos was still hot, still filling with the first generations of stars, still in its construction phase. Most of the matter in space was hydrogen and helium, the simplest elements, heavier elements. The kind that build planets and bones and coffee mugs did not yet exist in any meaningful amount. Galaxies in that era were supposed to be tiny, patches of gas, clumps of early stars, the cosmic version of a half-built town. What Webb showed instead was a row of completed cities. Each of these 6 galaxies, identified initially by a team led by Swinburne University of Technology in Australia, packed enormous amounts of stellar mass into compact regions. The estimate landed at roughly 10 billion solar masses each, with one candidate possibly larger than our entire Milky Way. To get a sense of that, picture a single galaxy holding more stars than every other galaxy in our local neighborhood combined. The deeper question was not just how heavy they were, it was how fast they got there. The follow-up analysis suggested something almost impossible. To reach those masses in that time, these galaxies would have needed to convert nearly all of their available gas directly into stars. almost a 100% efficiency. In modern galaxies, including ours, that number is closer to 5 or 10%. Most gas just floats around, blown by stellar winds, pulled by gravity, never becoming a star at all. Imagine a bakery that turns every single grain of flour, every drop of water, and every speck of sugar into perfect bread, with nothing wasted. Then imagine that bakery doing it at 10 times the normal speed. That was the kind of stellar production these objects implied. Some scientists tried to slow the panic. They argued the masses might be overestimated. Bright galaxies are tricky. If the light comes mostly from a few unusually massive stars, the total mass might appear larger than it really is. Other researchers suggested a hidden ingredient. Perhaps these were not pure galaxies of stars at all. Perhaps something else was buried in the center, generating extra light that made the whole object look heavier than it actually was. That something else turned out to be a clue we will return to, a possibility involving black holes, not the ordinary kind, something stranger, something seeded long before any star existed. For now, the 6 galaxies stood as a warning sign, a signal that the early universe was either far more productive than expected or operating under rules we had not yet learned. Either option carried a cost. The first meant rewriting our entire model of how stars form. The second meant rewriting something deeper, the framework, the starting conditions, the laws of cosmic growth. A team of researchers at Johns Hopkins University, led by Nashwan Sabti, pushed back against the wildest interpretations. They argued that adjusting the standard model to fit these galaxies broke other predictions, ones that matched older Hubble observations very well. Their conclusion was cautious. The problem might not lie in cosmology itself. It might lie in our understanding of how stars and galaxies behave in extreme environments. The debate continues today. Some defend the framework, others see cracks widening. But while astronomers argued about masses and redshifts, a quieter discovery was waiting in the same Webb data, a pattern not in size, not in brightness, but in motion. Galaxies spin. That part has been known for a century. Spiral galaxies, the kind that look like glowing pinwheels, have arms that wind around a bright central bulge. Some spin clockwise, others spin counterclockwise. The direction depends on which side you are looking at, which way the arms are coiled, and how the galaxy's disk is oriented relative to your line of sight. In a random universe, you would expect the count to be even, half spinning one way, half the other, like flipping a coin millions of times and watching the result settle into a perfect 50-50 split. That is not what James Webb showed. A computer scientist named Lior Shamir, an associate professor at Kansas State University, decided to test the count. He pulled images from the JWST Advanced Deep Extragalactic Survey, known by the short name JADES. This survey is a deep field. It stares at the same patch of sky for long periods, gathering light from extremely faint and distant objects. Webb's sensitivity makes the resulting pictures sharper than anything Hubble ever produced in those wavelengths. Shamir applied a quantitative method to the spiral galaxies in the field. He measured the curl of the arms, the orientation of the disks, and the direction of rotation for each one that was clear enough to analyze. 263 galaxies passed the cut, each one a small glowing pinwheel from the early universe. The result was striking. Roughly 2/3 of the galaxies rotated clockwise relative to our point of view. Only about 1/3 rotated counterclockwise. That is not a coin flip. That is a coin landing on the same side 2 times out of 3, over and over, across hundreds of independent throws. Statistically, the odds of seeing that pattern in a truly random universe are very small. Shamir made a point about how visible the asymmetry is. He said the analysis was done with quantitative tools, but the difference is so obvious that anyone looking at the image can see it without specialized training. No fancy calculations needed, just eyes and a finger to point. The natural first reaction is to suspect a mistake. Maybe the survey only looked at a small region of the sky. Maybe the orientation of the field happened to favor one direction. Maybe the human or computer process for classifying spirals had a built-in bias. Each of these had to be checked. Each one was: the Jade-S field happens to sit near the galactic pole, the direction perpendicular to the disk of our own Milky Way. That is convenient, because it gives a clean line of sight away from the dust and stars of our home galaxy. The asymmetry held up across multiple methods of measurement. It also showed up in earlier Hubble ultra-deep field data, although with smaller numbers. Webb simply confirmed the trend with a much larger and clearer sample. The published paper appeared in monthly notices of the Royal Astronomical Society in March of 2025. The title was simple. The implication was anything but. Either galaxies in the early universe really do prefer one direction, or our entire system for measuring distances and motions in deep space has a hidden flaw. Both options are dangerous. One rewrites cosmology. The other rewrites every distance measurement we have made in the last 50 years. And the explanation Shamir offered for the first option was even stranger than the discovery. The number to remember is 2/3. Out of 263 galaxies clear enough to study, roughly 175 rotated clockwise from our viewing angle. Roughly 88 rotated the other way. The gap is wide, not subtle, not borderline. Anyone scrolling through the images can see the lean by eye. In statistics, this kind of imbalance gets a label, a preferred axis. The phrase sounds harmless. Its meaning is enormous. A preferred axis means the universe has a direction, not a random scatter of motions, not an even distribution of spin, a built-in tilt, something woven into the structure of space itself, present from the earliest moments, carried through the formation of galaxies, surviving across 13 billion years of cosmic evolution. This idea cuts against one of the deepest assumptions in modern physics. The cosmos is supposed to look the same in every direction. That assumption is called isotropy. Isotropy means no spot in the universe is special, no angle gets more matter than another, no direction wins. Combine it with homogeneity, the idea that matter is spread evenly when you zoom out far enough, and you get the foundation of the Standard Model, the math of general relativity, the predictions of the Big Bang, the structure of the cosmic microwave background. All of it leans on isotropy. Webb's spinning galaxies poke a hole in that pillar. If a real cosmic preference for one rotation direction exists, then the universe has a memory of something earlier, a condition baked in before galaxies formed. A few researchers immediately raised the obvious objection. The universe is huge. Webb sampled a tiny window. Could the asymmetry be local, restricted to that one region of sky, rather than universal? Possible. But Shamir noted that similar patterns had appeared in older Hubble data, in different fields. A small clue here, a bigger clue there. The trend keeps reappearing wherever you point a sensitive enough telescope at distant galaxies. There are other strange features of the cosmos that already hint at directional preferences. The cosmic microwave background, that faint glow left over from the first hundreds of thousands of years after the Big Bang, contains odd alignments of hot and cold spots that some researchers have nicknamed the axis of evil. Large-scale flows of galaxy clusters, sometimes called dark flow, also seem to point in particular directions. Each of these results carries its own controversy. Each one alone is easy to dismiss. Stack them together and a pattern emerges. The spinning galaxy result is the cleanest of them. You do not need complex mathematics. You can see it in the pictures. If the asymmetry is real, the implications stretch far beyond astronomy. It would mean the universe carries a fingerprint of conditions that existed before galaxies formed. A rotation, a tilt, a kind of cosmic handedness. Physicists would have to explain where that handedness came from. One answer is mundane and almost boring. The Doppler effect, caused by our own galaxy's motion through space, could be making galaxies that spin opposite to the Milky Way appear slightly brighter and therefore overrepresented in our images. If true, Webb is not seeing a cosmic asymmetry. It is seeing a reflection of our own motion. The other answer is not boring at all. It says the universe was born spinning, and if the universe was born spinning, something must have been spinning before it. The first time you hear the idea, it sounds like a mistake. The universe is supposed to be everything. There is no outside, there is no before. How can everything spin? Spin around what? Yet the math allows it. General relativity, the framework Einstein finished a century ago, can describe a rotating universe. As far back as the 1940s, the mathematician Kurt Gödel showed that the equations have solutions in which the entire cosmos turns slowly around a global axis. Most physicists treat such solutions as curiosities, mathematical possibilities, not physical realities. But the equations do not care about taste. They allow it. A rotating universe would behave strangely. Light traveling around the rotation axis would bend in unusual ways. The flow of time itself, in extreme cases, could fold into closed loops, allowing in principle paths that return to their own past. Gödel found this disturbing enough that he used it as evidence the equations needed something extra. Decades passed. The idea drifted to the edges of cosmology. The Big Bang model, with its uniform expansion in all directions, took center stage. Spin became a footnote. Then Webb arrived, and the spinning galaxies showed up. If the universe really has a preferred axis, the cleanest explanation is that the universe itself was rotating from the start. The rotation would have imprinted a direction on the early matter. Galaxies, forming from that matter, would inherit a preferred spin, not perfectly, because gravity and chaos can overwhelm small biases, but as a statistical lean, 2/3 clockwise, 1/3 counterclockwise, would fit that picture. The number is small enough to look subtle, large enough to be real. This is where things get controversial. A rotating universe demands an external reference, something outside our cosmos for the rotation to be measured against. In ordinary physics, that requirement is hard to meet. The universe is, by definition, all of space and time. There is no observer floating beyond it with a compass and a stopwatch. Some physicists swat the idea away with that single objection. Others think it is a clue. They argue that a rotating universe makes sense if our universe is not the only one, if something larger contains it. If our cosmos is one bubble in a foam of bubbles, or one room in a much bigger structure. The second possibility is even bolder. If our universe is rotating relative to a larger frame, and if the rotation came from somewhere, then the source of the rotation might be the most extreme object in nature. A black hole, specifically a black hole in some other, larger universe, where matter falling inward formed a new region of space that became our cosmos. That sentence sounds like science fiction. It is not. It is a real proposal, with serious physicists behind it. The next chapter is where the strangeness deepens. Because if our universe was born from the inside of a black hole, the consequences ripple through everything. The arrow of time, the expansion of space, the reason the cosmic microwave background looks the way it does. Even the fact that we can ask the question at all. For 13 billion years, light has been carrying messages from the early universe. Webb is the first instrument careful enough to read the handwriting. And the handwriting is starting to look like it belongs to something we never expected to meet. The theory has a name: black hole cosmology. Sometimes it is called Schwarzschild cosmology, after the German physicist Karl Schwarzschild, who first solved Einstein's equations for the region around a black hole back in 1916. The idea is simple to state and dizzying to absorb. Our entire observable universe sits inside the interior of a black hole that exists in some larger, parent universe. Imagine a black hole. From the outside, it looks like a dark sphere with a sharp boundary called the event horizon. Cross that boundary and you cannot return. From the inside, however, the geometry stretches in unusual ways. Space and time swap roles. The center of the black hole is not a place, it is a future event, unavoidable, like the next moment in your life. In black hole cosmology, That interior is not crushed into a point. Instead, it expands. Matter falling in does not collapse to a singularity. It bounces, rebounds, or transitions into a new region of space that grows outward in its own direction of time. From inside that new region, the bounce looks like a big bang. The expansion looks like cosmic inflation. The boundary of the parent black hole looks like the limit of the observable universe. If our universe formed this way, several of its strangest features start to make sense. The flatness of space, which has puzzled cosmologists for decades, fits naturally. Matter, falling into a black hole, arrives smoothly oriented. The expansion that follows would be uniform. The arrow of time, the fact that the future feels different from the past, also gains a source. Material crossing the event horizon of the parent black hole can only move inward. That one-way motion creates a built-in direction. Time inside the new universe inherits that direction. Yesterday is closer to the boundary, tomorrow is deeper inside, and the rotation of the parent black hole would imprint a preferred axis on the daughter universe, the same axis that Webb's galaxies appear to remember. Nikodem Poplawski, a theoretical physicist at the University of New Haven, has championed this idea for years. He told reporters covering the Webb result that he believed the simplest explanation for a rotating universe is that it was born inside a rotating black hole. He said he would be extremely excited if the findings held up. Most working cosmologists are not convinced yet. The idea has elegant features, but few testable predictions. It is also philosophically uncomfortable. It places our entire cosmos inside another cosmos, raising the obvious next question: what is the parent universe inside of? Some versions of the theory accept an infinite chain. Black holes in our universe spawn new universes. Those new universes spawn more black holes. Each cosmos is a node in an endless tree. Other versions try to close the loop, suggesting the whole structure is somehow self-contained. The picture is hard to picture. That is a feature, not a flaw. The standard Big Bang is also hard to picture. A point of infinite density expanding into existence is not an everyday image. We accept it because the math works and the predictions match observation. Black hole cosmology is asking for the same patience. Different math, same demand. Show us the predictions. Match them to the data. For decades, no observational test seemed within reach. Then Webb pointed at the Jades field, counted the spinning galaxies, and quietly delivered the first result that the theory had been waiting for: a pattern in the rotations, a preferred axis, a signal that the universe might remember its parent. Poplawski's version of black hole cosmology has a twist that makes the picture even stranger. He works with a modified version of general relativity called Einstein-Cartan theory. The change is technical. Standard general relativity treats space and time as smooth and curvable. Einstein-Cartan adds a property called torsion, a kind of twisting of space when matter has spin. In normal conditions, torsion is tiny. You will never notice it on Earth. But inside a black hole, where matter is compressed to extreme densities, the twist becomes powerful. According to Poplawski's calculations, torsion stops the collapse before it reaches a singularity. Instead of a point of infinite density, you get a bounce, a rebound. A new region of space opens up. That new region, in his framework, is a baby universe. So, black holes are doorways. Each one is a passage from a parent universe to a new one. The new universe inherits properties from its parent: the rotation, the mass, the arrow of time. From inside, observers see a cosmos expanding from a hot beginning. They call it their Big Bang. They build their telescopes. They wonder how it all started. They have no way of knowing they live inside a structure that, from the outside, is just one more dark sphere in an older sky. Poplawski wrote about this in detail. He pointed out something subtle about the arrow of time. The motion of matter through the event horizon of a black hole can only happen in one direction: inward. That asymmetry, he argued, gets passed to the baby universe through torsion. Time inside the new cosmos has a built-in direction inherited from the parent. Now connect that to Webb. If our universe was born inside a rotating black hole, the rotation axis of the parent gets stamped onto our cosmos. Galaxies forming inside our universe inherit a small bias toward one rotation direction, not absolute, statistical. 2/3, 1/3. Exactly the kind of imbalance Shamir found. When asked about the JWST result, Poplarski did not hold back. He said that a discovery of a preferred axis in the rotation of galaxies would support the theory of black holes creating new universes, and that he would be extremely excited if the findings were confirmed. That is a careful sentence. He did not claim victory. He pointed at the prediction his framework had made and said, "Here is the test. Here is the result. Here is the match." Other physicists are skeptical. Some argue that the apparent asymmetry could come from unrelated factors, selection biases, Doppler effects, the motion of our own galaxy. Each of these alternatives needs to be ruled out before the baby universe theory can be taken seriously. The honest answer right now is that the evidence is suggestive, not decisive. One paper, one survey, a few hundred galaxies. To prove the universe was born inside a black hole, we would need many more measurements, in many more fields, with many more telescopes. The work has already begun. Other teams are searching for similar asymmetries in different patches of sky. New surveys are planning to count rotation directions on samples of millions of galaxies, not just hundreds. The next decade will tell us whether the doorway theory survives. If it does, every black hole you see in a Webb image becomes more than a gravitational monster. It becomes a possible birthplace, a nursery, a door swinging quietly into a cosmos we will never visit. And while astronomers debated rotating universes and parent black holes, another crack was widening in the standard model, a crack that had nothing to do with spin, a crack in something more fundamental, the speed at which the universe is expanding. Edwin Hubble made one of the great discoveries of the 20th century. In 1929, he showed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. The cosmos was not static, it was expanding. The universe had a history, a beginning, a direction. The rate of that expansion got a name, the Hubble constant. It tells you how fast space itself is stretching. Measure it, and you can calculate the age of the universe, the rate at which galaxies separate, and the future evolution of the cosmos. For decades, scientists chased that single number. Better telescopes, better methods, more distant galaxies. Each new measurement pushed the precision further. By the early 2000s, the value seemed to settle around 70 kilometers per second per megaparsec, roughly 43 miles per second across each unit of cosmic distance. Then a problem appeared. Two different methods kept producing two different numbers. The first method uses the cosmic microwave background, the leftover glow from the early universe, just 380,000 years after the Big Bang. Combine those measurements with the standard model of cosmology, run them forward through Einstein's equations, and you get a Hubble constant of about 67.4 kilometers per second per megaparsec. The second method uses pulsating stars called Cepheid variables. These are special stars that brighten and dim on regular cycles. The cycle length tells you the star's true brightness. Compare that to how bright it appears, and you get the distance. Use that distance ladder to measure faraway galaxies, and you can calculate how fast they are moving away. This method gives a value of about 73. The two numbers should match. They do not. The gap is small in everyday terms, less than 10%. In cosmology, it is a chasm. A gap that size means the standard model is missing an ingredient, a force, a particle, a phase of the early universe that the equations have not accounted for. This puzzle got its name, the Hubble tension. For more than a decade, astronomers tried to close it. Maybe the Cepheid measurements were biased by crowded star fields. Maybe the cosmic microwave background analysis assumed something wrong about dark matter. Maybe a hidden source of error was inflating one number or shrinking the other. Adam Rees, a Nobel laureate from Johns Hopkins University and one of the discoverers of dark energy, led the team pushing the Cepheid method to ever finer precision. By 2019, his Hubble Space Telescope measurements had narrowed the uncertainty enough that the disagreement could no longer be blamed on noise. Then Webb launched. The new telescope was sharper. Its infrared eyes could pierce the dust and crowding that had haunted Hubble's measurements. If the Cepheid numbers were wrong, Webb would expose the error. If the measurements were right, the tension would be confirmed. Webb pointed at the same galaxies Hubble had studied. It measured the same stars. It applied 3 different methods, including new ones that did not even use Cepheids. The team gathered the largest sample of Webb data collected during the telescope's first 2 years in space. The result arrived in late 2024. The numbers stood. The methods agreed. The error was not on Hubble's side, Rees put it plainly. The discrepancy between the observed expansion rate of the universe and the predictions of the standard models suggests that our understanding of the universe may be incomplete. Webb had ruled out the easy escape. The tension was real. The universe was not behaving the way the equations said it should. A puzzle that had simmered for a decade had just become a permanent crack. To grasp why the Hubble tension matters, picture a recipe. The standard model of cosmology is the cookbook the universe has been following for 13 billion years. Take some hydrogen, add dark matter, sprinkle in dark energy, let it expand, stir gravity. The cake comes out looking like the cosmos we see today. If the recipe is correct, every measurement of expansion should give the same number, no matter where in time you look. Measure the early universe through the cosmic microwave background. Measure the local universe through nearby supernovae. The 2 values should match. They do not. The local universe is expanding faster than the early universe predicts. Roughly 9% faster. That is the tension. 9% does not sound like much. Try this comparison. Imagine a clock that loses 1 second every 20 seconds. That clock cannot be ignored. Multiply across a day, a week, a year, and you end up in a different time zone. The cosmic version is similar. Apply a 9% error across 13 billion years, and you get galaxies in places they should not be, ages that do not add up, and a future timeline that drifts away from prediction. So either the early universe measurement is wrong, or the late universe measurement is wrong, or the model connecting them is wrong. Webb has now ruled out the first 2. That leaves the third. What could be missing? Some theorists suggest a brief burst of repulsive energy in the early universe, something that puffed the cosmos up faster than standard inflation predicts, then disappeared. This is sometimes called early dark energy. Add this ingredient, and the early universe expansion rate changes just enough to match the local measurements. The trouble is, no one has seen early dark energy. No particle, no field, no clean signal. It is a name attached to a placeholder. The recipe demands an ingredient that has never been weighed. Other theorists go further. They argue that maybe the dark energy we already know about is not constant. Perhaps it changes over time. Recent results from the Dark Energy Spectroscopic Instrument, a survey mapping huge swaths of the sky, hint that dark energy might be weakening in our era. If true, that would rewrite the future of the universe. The expansion would not accelerate forever. It would slow, stall, perhaps reverse. Still, others propose changes to gravity itself. Maybe Einstein's equations need a modification at large scales, a correction term that only matters across billions of light years. Modified gravity theories have a long history. Some of them survive, most of them die. None has yet become the consensus replacement. A few researchers suggest something even stranger. Perhaps the universe has different expansion rates in different regions. We might live in a giant void, a slightly underdense region where things expand a bit faster than the cosmic average. Outside our void, the universe could be slower. The Hubble tension could be partly a local effect. Webb is helping test some of these ideas. Its surveys of distant galaxies are mapping the cosmic web on scales that older telescopes could not reach. Each new measurement either tightens the tension or offers a new hint about what might fix it. So far, nothing has fixed it. The crack is wider, not narrower. Adam Rees and Mark Kamionkovsky, also at Johns Hopkins, have noted that resolving the tension could reveal new insights into other discrepancies that have come to light. The cosmologists are not just chasing one mystery, they are watching several mysteries pile up: the early galaxies, the rotation asymmetry, the expansion rate. They might be related, they might be telling the same story in different languages. And in the middle of all this, Webb made another discovery, a new kind of object, tiny, red, glowing, everywhere. For years, the comfortable answer to the Hubble tension was that one of the measurements must be wrong. Not the model, not the universe, the instruments, specifically the local measurements that depended on Cepheid variable stars. Cepheids live in the disks of younger galaxies, crowded regions, dust everywhere, other stars nearby. When the Hubble Space Telescope tried to measure a single Cepheid, it caught light from all its neighbors too. The brightness might be a little off, the distance might be slightly wrong. Multiply that by hundreds of stars across the cosmic distance ladder, and you can imagine a small bias creeping into the final number. This is the argument George Efstathiou and other senior cosmologists made for years. They suggested that with such crowded fields, even the famous resolution of Hubble was not enough. Every Cepheid was overlapping with other stars. The measurements were being polluted. If true, the tension would dissolve. The early universe and the local universe would agree. The standard model would survive. Webb was the test. With its larger mirror and infrared eyes, Webb could see through dust. It could resolve individual stars in galaxies that were just blurs in older images. If the Hubble Cepheid measurements had been biased by crowding, Webb would prove it. Adam Rees and his team got to work. They did not just remeasure a few Cepheids. They covered roughly a third of Hubble's full sample of distant galaxies. They used a galaxy called NGC 4258 as an anchor point because its distance is known by an independent method. They cross-checked everything. Then they applied not just one method but three: the Cepheid technique, a second method using carbon-rich stars, a third using the brightest stars in old galactic populations called the tip of the red giant branch. 3 independent methods, run on the same Webb data. The results aligned. Webb's measurements matched Hubble's measurements within 2%. That is far smaller than the 8 or 9% gap of the Hubble tension itself. Webb confirmed that the local universe is indeed expanding at roughly 73 kilometers per second per megaparsec. Rees summarized the conclusion in a single sentence: with measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe. Translation: the instruments are fine, the methods are fine, the math connecting them is broken. Wendy Friedman of the University of Chicago, leading a separate team, ran her own multi-pronged Webb analysis using 3 different types of stars. Her results showed an interesting wrinkle. 2 of the 3 star types gave an expansion rate that matched the early universe prediction. The third, the same Cepheids that Rees uses, gave the higher local value. Friedman concluded that the disagreement between the methods might point to a hidden error in one of the distance techniques rather than in cosmology itself. Rees pushed back. Saul Perlmutter, another Nobel laureate who reviewed Friedman's preprint, said the results suggested there might be a tension just within the star-based methods themselves. The debate is alive. The numbers are precise. Different techniques disagree. The most striking thing about the discussion is what is no longer being said. Nobody is claiming the tension came from a simple measurement error. That excuse is dead. Webb killed it. What replaces it is harder to swallow. Either the standard model is missing a major ingredient, or the universe is doing something we do not yet have words for, possibly both. Rees himself is part of the team that won the 2011 Nobel Prize for discovering dark energy, a force nobody predicted that turned out to be making up most of the universe. He has lived through one revolution already. Now he is watching a second one approach. And while cosmologists argued about expansion rates, Webb pointed its eyes at empty patches of early sky and found something that nobody had predicted at all. The first sightings looked like noise, small, faint, red specks scattered across Webb's deep field images. Astronomers initially assumed they were just unusually colored galaxies, distant and dust-reddened, the kind of background detail you log and move past. Then someone noticed how many there were, and how strange they looked. The objects were nicknamed little red dots. Astronomers love simple names. The dots are tiny, a few hundred light-years across at most. Compare that to the Milky Way, which spans roughly 100,000 light-years. A little red dot is to our galaxy what a marble is to a stadium. They glow with a deep red color, suggesting they are either heavily obscured by dust or extremely far away, red-shifted by the expansion of the universe. They appear in vast numbers in Webb's deep fields. 3 to 4 out of every 100 galaxies in some early universe samples look like one. That is not rare. That is everywhere. They show up around 600 million years after the Big Bang. They peak in number at around 800 million years. By 1.5 billion years after the Big Bang, they mostly vanish. Whatever they are, they had a beginning, a reign, and an end. A short geological era of the cosmos that we never knew existed until Webb pulled back the curtain. The first interpretation was that the dots were active galactic nuclei, tiny galaxies hosting growing supermassive black holes. The black holes pulled in gas. The gas heated up. The heat released enormous radiation. That would explain the brightness despite the small size. But the standard signatures of active galactic nuclei were missing. No clear X-ray emission, no strong variability over time, no flat infrared spectrum. The dots looked like quasars in some ways and like pure starlight in others. Then Dale Kuchevsky and his colleagues found high-velocity gas around several of the dots, speeds of 2,000 to 4,000 kilometers per second. That kind of motion is rare for ordinary galaxies. It is common around growing black holes. The gas is being whipped by the gravitational pull of an enormous central object. Interpretation shifted again. Maybe the dots really were powered by black holes, just a kind we had not seen before. Compact, hidden, surrounded by enough material to muffle their X-rays. The number of dots became the next puzzle. If they all contained supermassive black holes, the early universe must have produced an enormous population of these monsters very quickly, far more than standard models predicted. Some researchers connected the dots, so to speak, with the broader puzzle of impossibly massive early galaxies. Maybe the unexpectedly heavy galaxies and the little red dots were related. Both pointed to a population of black holes that had grown faster than theory allowed. Both suggested that the recipe for the early universe was missing an ingredient. A team led by Fabio Pacucci at Harvard proposed an explanation. The dots could form naturally inside dark matter halos with very low spin. Slowly rotating halos would let gas collapse straight inward, creating dense, compact red sources. The math fit reasonably well with what Webb was seeing. Other teams went further. They suggested the dots might be the visible signs of a population of primordial black holes, formed not from collapsing stars but from the early universe itself. The dots had become a doorway to a deeper question. Where did the first black holes come from? And the answer kept circling back to a possibility that older cosmology had quietly dismissed. Maybe black holes did not form from stars. Maybe they came first. One of the strangest features of the little red dots is not how they appear, it is how they disappear. Surveys covering the period from 600 million to about 1.5 billion years after the Big Bang find them everywhere, field after field, image after image. Then, somewhere around the 1.5 billion year mark, the population thins. Within a few 100 million more years, The dots are essentially gone. That is a sharp boundary in cosmic terms. Whatever the dots are, they were a phase, a chapter. Something turned them on, something turned them off. The simplest explanation is that they evolved into something else. Gas got blown out, dust cleared. The compact objects grew larger, brighter, and looked like more familiar galaxies. The dots did not vanish so much as graduate. They transformed. That story fits some observations and conflicts with others. Massive, quiescent galaxies, the elderly retirees of the cosmos, sit quietly in the local universe. If the dots evolved into anything, those retirees are reasonable candidates. Recent results from a Webb program called Rubies, led by Anna de Graaf and Gabriel Brammer, suggest that some apparent quiescent galaxies in the early universe may have been miscounted, raising the number of confirmed massive resting galaxies by roughly a factor of 10. Other researchers see something more ominous. They argue the dots could be the remnants of an entirely separate cosmic process, one that does not connect smoothly to later galaxy populations at all. A class of objects with no surviving relatives, a dead branch on the tree of cosmic structure. The X-ray puzzle deepens the mystery. Active galactic nuclei usually emit huge amounts of X-rays. The dots, mostly, do not. A few have been detected with weak X-ray signals. One in particular, catalogued by NASA's Chandra Observatory under a long technical name, sits exactly at the location of a Webb little red dot. The X-ray energy resembles a quasar. The match was reported in late 2025 and remains one of the strongest links between the dots and supermassive black hole activity. But most dots stay X-ray dark. Their light spectrum looks like a black hole eating gas in some ways, like compact star formation in others, like something the textbooks have not described in still others. A theory called the black hole star, developed in part by researchers studying the data, proposes a striking picture. The dots are not galaxies in the usual sense. They are enormous, dense clouds of gas, with a growing supermassive black hole hidden inside. The gas absorbs the X-rays, which is why we do not see them. The star-like spectrum is the gas itself, glowing under the energy of the black hole within. Imagine a star the size of a galaxy, with a black hole as its heart. That is the picture. If the black hole star idea is correct, the dots were a cosmic stage, a brief moment when supermassive black holes were forming inside dense clouds, before the clouds dispersed and revealed the monsters. Once the gas blew off, the structures became normal galaxies with active centers. The dots disappeared because they were a transitional phase, a short window in cosmic time, a glimpse at the moment supermassive black holes were being built. Webb caught it because Webb could see in infrared what nothing else could. If true, the dots are the closest thing astronomers have to a baby picture of a supermassive black hole, the kind of object that sits at the center of nearly every modern galaxy, including ours. Their formation has puzzled scientists for decades. Webb may have just opened the maternity ward. The phrase sounds like a contradiction. Black holes eat light. Stars produce it. How can one be the other? The answer is geometry. A black hole star is not a single object. It is a system. At the center, a growing supermassive black hole. Around it, an enormous cloud of gas. The gas falls inward, releases gravitational energy as heat and light, and shines out across the cosmos. From far away, the system looks like a glowing ball of gas, like a star. The black hole inside is hidden. The numbers are extraordinary. Some of the proposed black hole stars stretch a few hundred light-years across. The gas cloud weighs millions of times the mass of the Sunday. The black hole at the center may already weigh between 100,000 and a few million solar masses. All of this just 600 million years after the Big Bang. For comparison, the supermassive black hole at the center of our own Milky Way, called Sagittarius A star, weighs about 4 million solar masses. It has been growing for roughly 13 billion years. The black hole stars in Webb's images appear to be reaching similar masses in less than a billion years. That is not enough time. Not under normal physics. Black holes grow by pulling in matter, but the radiation from the infalling material pushes back. There is a natural speed limit on growth, called the Eddington limit. At that limit, the radiation pressure balances the gravitational pull, and the black hole cannot accrete faster. To explain the early black holes, scientists have proposed several escapes from this speed limit. Some argue the early black holes simply broke the limit, accreting at super Eddington rates for short bursts. Others suggest the early black holes started big, not born from collapsing stars, but formed directly from the collapse of huge gas clouds. These would be heavy seeds, perhaps 10,000 to 100,000 solar masses at birth, heavy enough to bypass the slow build-up phase entirely. Then there is the most radical idea. The early black holes were not formed from gas at all. They were formed from the first moments of the universe itself. These are called primordial black holes. Their existence was first proposed by Yakov Zeldovich and Stephen Hawking in the 1960s and 70s. The idea is that in the chaotic conditions of the first second after the Big Bang, dense pockets of energy could have collapsed directly into black holes. Some would be tiny, evaporating long ago. Others could be massive, still around today, hidden among the galaxies. If primordial black holes exist, they could have served as the seeds for early galaxies. Drop 1,000 solar mass primordial black hole into a region of dense gas at high redshift. Surround it with a dark matter halo, let it grow at extreme rates, and you can build 100 million solar mass black hole within a few 100 million years. That timeline matches what Webb sees. The math has been worked out by multiple teams. A paper by Zhiqiang Shen and colleagues at the Hong Kong University of Science and Technology used a Bayesian framework to model how primordial black holes could explain the high redshift Webb galaxies. Their preferred model fit the observations cleanly. Another paper, by A. D. Dolgov, building on a 30-year-old conjecture with Joseph Silk, argued that supermassive primordial black holes could naturally seed both the early galaxies seen by Webb and the supermassive black holes seen at the centers of galaxies today. The implication is staggering. If the standard story of black holes is wrong, then nearly every galaxy in the cosmos may be built around a primordial seed, something older than the first star, something that helped shape the structure of the cosmos before structure even existed. And the next clue arrived in X-rays. The Chandra X-ray Observatory has been orbiting Earth since 1999. It is a NASA mission, smaller and less famous than Webb, but its eyes are tuned to a different kind of light. X-rays are produced by extreme conditions: hot gas, exploding stars, material falling onto neutron stars, and black holes. Chandra's archive holds millions of X-ray sources, mapped across decades of observations. When Webb began identifying little red dots, astronomers naturally checked whether any of them matched known X-ray sources in Chandra's catalogue. Most did not. The dots were stubbornly X-ray quiet. Then one match appeared, a source in the extended growth strip, a heavily studied patch of sky, sitting in exactly the same position as a little red dot identified by Webb. The X-ray source had been catalogued under a long technical name from the All-Wavelength Extended Growth Strip International Survey. It had been recorded years before anyone knew the dot was there. The X-ray energy fingerprint matched the kind of signal expected from quasars. Quasars are galaxies hosting extremely active supermassive black holes, often triggered by mergers. They produce some of the brightest emissions in the universe. Finding a quasar-like X-ray signal at the location of a tiny red dot from the early universe was a major link. The result was reported in late 2025. It strengthened the theory that little red dots are powered by supermassive black holes, even if most of them do not show X-rays directly. The single match suggested that the X-rays were being produced. They were just being absorbed somewhere along the way, by dust, by the surrounding gas cloud, by the black hole star envelope. If the framework is correct, the X-rays we are seeing in this single dot are leaking through a thin spot in the gas. Most other dots are wrapped too tightly, hiding their inner monsters from Chandra. Webb sees the warm glow of the cloud. Chandra cannot pierce through to the heart. That picture has a quiet elegance. A black hole hidden inside a cloud, producing energy that powers the cloud's brightness, while shielding itself from the X-ray detectors that should otherwise expose it. Like a fire wrapped in a thick blanket, you feel the warmth. You do not see the flame. The discovery does more than strengthen one theory. It opens a path. As more X-ray observations are made of little red dot positions, more leaks may be detected. Each leak provides direct evidence of a hidden black hole. Each detection helps separate the black hole stars from other possible explanations. It also raises a difficult question. If black hole stars existed in the early universe, why are there no clear examples today? The simple answer is that the surrounding gas dispersed. The clouds were temporary. Once they blew away, the central black holes became visible as ordinary active galactic nuclei, or quasars. The black hole star phase ended when the cosmos became too thin to hide the monsters. That is a tidy story. It may also be too tidy. Some researchers note that the observed transition from little red dots to standard galaxies is not as clean as the simple model predicts. Some dots seem to persist longer than expected. Others have spectral features that do not match either pure black hole star or pure galaxy templates. The category may be more diverse than the early discoveries suggested. Webb is not done with them. New surveys will catalogue thousands more dots in the coming years. Spectrographs will pull apart their light into chemical fingerprints. X-ray follow-ups will hunt for more leaks. For now, the little red dots remain one of the most surprising discoveries in modern astronomy. They were not predicted. They appeared in nearly every Webb deep field. They challenge standard galaxy formation models. They may rewrite the story of how supermassive black holes came to be. And while the dots argued about their identity, 300 more strange objects waited in another patch of sky. A team at the University of Missouri, led by astronomy professor Haojing Yan, decided to ask a simple question. How many bright objects appear in Webb's infrared images of the deep universe that should not be that bright? They expected a handful, maybe a few dozen mistakes that would resolve into normal galaxies on closer inspection. They found 300 objects, scattered across Webb's fields, brighter than the standard model said they should be. Each one a candidate for being an extremely early galaxy, glowing harder than the equations allowed. The team published their work in 2025. Yan was careful with his language. He called them candidates. He said that even if a few of them turned out to be what the team suspected, the discovery could challenge current ideas about how galaxies formed in the early universe. Just a few. That is how thin the line is. The reason the brightness matters comes back to a familiar theme. Bright early galaxies require intense star formation, or they require additional sources of light beyond stars. Either option breaks part of the standard picture, either rewriting how stars formed or admitting the early universe had ingredients we have not catalogued. The 300 objects share a few traits. They are small, they are red, suggesting either dust reddening or extreme distance. They glow more brightly in the infrared than older models predicted. Some of them may be little red dots, others may be a different population entirely. Confirming their nature is slow work. Identifying objects in space, as Yan said, is not instant. It takes spectroscopy. It takes follow-up observations with multiple instruments. It takes arguing with colleagues, defending the data, ruling out alternatives. The 300 candidates will be studied for years. Some will turn out to be foreground objects, projected onto the early universe by chance alignment. Others will turn out to be active galactic nuclei, masquerading as bright galaxies. A few will likely survive every test and stand as confirmed early universe puzzles. Even if only 10% of the 300 hold up, that is 30 objects. 30 more entries on the growing list of things in the early cosmos that do not match prediction. The pattern matters more than any single object. Webb keeps finding too many bright things, too early. Different surveys, different teams, different techniques, all returning the same kind of result. Each discovery alone would be controversial. Stacked together, they form something harder to dismiss. A senior cosmologist, asked about the trend, used a phrase that has begun to circulate in the field: excess light. The early universe seems to have produced more light in more places than the standard recipe allows. Whether that excess comes from unusually bright stars, primordial black holes, dark matter interactions, or some unknown source, the data keeps pointing at a missing ingredient. That phrase, missing ingredient, has become a quiet refrain in modern cosmology. The Hubble tension needs one. The early bright galaxies need one. The little red dots need one. The rotation asymmetry might need one too. A reasonable scientist looks at 4 open puzzles and asks whether they all need the same hidden ingredient or whether each needs its own. Both possibilities feel uncomfortable. A single missing ingredient that explains everything would be revolutionary. Multiple missing ingredients, each tucked behind a different mystery, would be even more humbling. The recipe was supposed to have a few simple components. It is starting to look like a kitchen drawer with several unlabeled jars, and there is a final wrinkle to the bright early galaxy problem. A wrinkle that reaches deeper than ingredients, or tensions, or rotations. Some of the galaxies may be older than the universe itself. The phrase sounds like a logical impossibility. The universe is roughly 13.8 billion years old. Nothing inside it can be older than that. The math is simple. Yet several Webb observations have produced age estimates for individual galaxies that bump uncomfortably against, or even past, the cosmic age limit. The estimates come from analyzing the chemical composition and stellar populations of the galaxies. Old stars produce specific spectral signatures. Heavy elements take time to form, requiring cycles of star birth, death, and rebirth. By measuring the metal content and stellar ages of a distant galaxy, astronomers can estimate how long it has been forming stars. In some Webb images, that estimate exceeds the time available since the Big Bang. The conclusion is not that those galaxies are literally older than the universe. That would violate causality. The conclusion is that something in our measurement chain is broken. Either the distance to the galaxy is wrong, or the age estimate is wrong, or the timeline of cosmic expansion is wrong. This is where some researchers have started exploring more radical ideas. One of them is Rajendra Gupta, a researcher whose work has gained attention by proposing that the universe may be far older than the standard age. In a series of papers, Gupta has argued that the cosmos could be roughly 26 to 27 billion years old, nearly twice the standard estimate. That sounds outrageous. It almost certainly is. But Gupta's reasoning is detailed enough to be worth following. He combines 2 ideas. The first is called covariant coupling constants. The constants of nature, like the strength of gravitational interactions and the speed of light, might shift very slightly across cosmic time. If they do, the relationships between observed redshifts and distances would change. The second is an older idea called tired light, which suggests that photons gradually lose energy as they travel through space, shifting toward the red end of the spectrum without requiring expansion. Tired light has been mostly discarded by mainstream cosmology because it fails to match certain other observations. The cosmic microwave background, the patterns of galaxy clustering, the way distant supernovae fade. Each of these observations behaves like cosmic expansion is real, not a static universe with tired photons. Gupta argues that combining tired light with shifting constants can match all the observations, and produces an older universe in which Webb's mature early galaxies make sense. They look mature because they are mature. The universe simply gave them more time. The paper claims that the resulting cosmos does not require dark matter to exist. That is a remarkable claim. Dark matter has been the invisible scaffolding of the standard model for decades. Removing it would simplify some puzzles and explode others. Most cosmologists are skeptical. The standard model has been carefully tested across an enormous range of observations. Dark matter signatures show up not just in galaxy rotation curves but in gravitational lensing, in the cosmic microwave background, in the formation of cosmic structure. Removing dark matter requires explaining all of those effects through other means. Yet, the existence of mature galaxies in the early universe creates an opening. If standard physics cannot fit them in, alternative physics gets a hearing. The mainstream response has been to look for ways to rescue the standard model. Maybe early stars were brighter than expected. Maybe primordial black holes provided early seeds. Maybe dust patterns made galaxies look older than they are. Each fix is plausible. None has one universal agreement. The galaxies older than the universe are a clue. They are also a warning. They sit at the edge of what current cosmology can explain. They push researchers toward asking whether the framework, not just the details, might need to change. And the next chapter sharpens that question. Because if the universe is not what we thought, then perhaps its most fundamental ingredient, the invisible matter that makes up most of its mass, might not be what we thought either. When Rajendra Gupta proposed his older universe theory, he leaned heavily on a concept that most working physicists treat as a mathematical curiosity. The constants of nature, the supposedly fixed numbers that govern how the cosmos behaves, might not be fixed at all. The constants you have heard of include the speed of light, the strength of gravity, and the charge of an electron. Together, they set the rules for how matter interacts. Atoms hold together because of these numbers. Stars burn because of them. Light travels at its measured speed because that speed is woven into the fabric of physics. The standard assumption is that these numbers have been the same since the Big Bang. The universe might be expanding, galaxies might be drifting apart, but the rules themselves do not change. A meter is a meter, a second is a second, a kilogram is a kilogram, everywhere and always. The covariant constants idea questions that assumption. It asks whether the constants might shift slightly across cosmic time, in coordinated ways that preserve some deeper relationship between them. Gupta's framework, sometimes shortened to CCC, lets several constants drift together so that observed quantities like atomic spectra and stellar luminosities still match predictions, while the underlying numbers slowly evolve. Most physicists consider this a long shot. Decades of experiments have tested whether constants drift, and the limits are tight. Atomic clocks, distant quasar spectra, and ancient natural nuclear reactors on Earth all place strong constraints. If the constants do drift, the drift is small, but small does not mean zero. And small drifts, integrated across 13 billion years, can produce noticeable effects. If the strength of gravity has changed slightly, then the rate at which galaxies cluster together would change too. If the speed of light has changed, then the relationship between distance and travel time gets rewritten. If multiple constants drift in coordinated ways, the cumulative effect on cosmic measurements could be significant. Gupta's argument is that combining drifting constants with the older, tired light idea produces a coherent cosmos that matches Webb's observations without breaking earlier data. The galaxies look mature because they are mature. The mass estimates are not wrong. The redshifts are not misinterpreted. The universe simply had more time to build them. That extra time, in his framework, comes from reinterpreting the redshift of distant galaxies. Standard cosmology treats redshift as evidence of expansion. Gupta splits it into two contributions. Some redshift comes from real expansion. Some comes from photons losing energy as they travel through space. The tired light effect. If only part of the observed redshift is due to expansion, then the inferred ages of galaxies change. The math of distance and time gets rewritten. The universe stretches further into the past. How much further? Gupta's papers argue for roughly 26 to 27 billion years, almost double the standard age. That figure sounds extreme. It is, by mainstream standards, but the framework gets one thing right that the standard model struggles with. The mature early galaxies fit naturally. They have time to form. Their masses and chemistry are not anomalies. They are just normal galaxies that have been forming stars for billions of years longer than the standard model allows. The pushback from mainstream cosmology has been swift. Critics point out that an older universe with drifting constants would leave fingerprints in many other places. Atomic spectra from ancient quasars should look different. Patterns in the cosmic microwave background should not match standard predictions. Element abundances from the early universe should be off. Gupta and his collaborators argue that their model can accommodate these constraints. Critics argue it cannot. The debate continues in technical journals. Most working cosmologists remain skeptical, but the conversation now happens in real conferences, not in margins of fringe blogs. What changed? Webb's data. Mature early galaxies opened a door that older theories had closed. The idea is almost 100 years old. In the 1920s, just as Edwin Hubble was building the case for cosmic expansion, the Swiss astronomer Fritz Zwicky proposed an alternative. Maybe distant galaxies were not really moving away. Maybe their light was just getting tired during the long journey. The proposal had a logic to it. Photons, traveling across vast distances, might lose energy through some unknown interaction with intervening matter or with space itself. Lost energy means lower frequency. Lower frequency means a shift toward red. That red shift could be mistaken for cosmic expansion. Zwicky's idea was tested and largely rejected over the following decades. The cosmic microwave background, the brightness fade of distant supernovae, and the time dilation observed in supernova light curves all behave like real expansion. Tired light has trouble matching all of them simultaneously. By the 1970s, the mainstream had moved on. The Big Bang and cosmic expansion had won. Tired light became a footnote, mentioned mostly in textbooks, as an example of how alternative theories can fail. Webb has revived the conversation, not the original tired light theory, which still struggles with most of the original objections. A modernized version, often combined with other ideas like covariant constants, that aims to address the failures of the simple version while preserving its core insight. Maybe some fraction of the observed redshift in distant galaxies comes from photon energy loss, not just expansion. The motivation is the same as it was a century ago. If standard expansion does not match what we see, alternative explanations get a fresh look. The most common objection to tired light is the cosmic microwave background. That faint glow, observable in every direction, has a temperature of about 2.7 Kelvin and matches a perfect thermal spectrum to extraordinary precision. Standard cosmology explains this as the cooled remnant of light from the early universe, stretched by expansion. Tired light has a harder time matching it because photons losing energy through scattering would smear the spectrum. Modernized versions try to handle this by being careful about which interactions cause the tiring. Some only affect certain wavelengths. Others happen only during specific cosmic epochs. Each tweak adds complexity. Each complexity reduces the simplicity that made the original idea attractive. The supernova test is another challenge. Distant supernovae fade more slowly than nearby ones. The standard explanation is time dilation, the same effect that Einstein's relativity predicts. As the universe expands, time itself appears stretched for distant events. Light curves stretch with it. Tired light, in its simplest form, predicts no time dilation. The light curves should look identical, just dimmer and redder. Observation shows the dilation. The supernova test was a major reason tired light fell from favor. Yet the early Webb galaxies have created enough discomfort with the standard model that some researchers are willing to revisit even old, partly discredited ideas. If a hybrid model with a small tired light contribution can explain mature galaxies in the early universe, it might be worth keeping on the table even if it has problems elsewhere. The honest assessment is that mainstream cosmology has not embraced tired light. Most papers proposing it remain at the edges of the field, generating attention but not consensus. The Webb data is uncomfortable for the standard model, but most cosmologists see the discomfort as a sign that the standard model needs modification, not replacement. Tired light remains a minority view. Its return to the conversation is a symptom of the broader unease in cosmology, not a sign that it is winning. The galaxies older than the universe might find an explanation in dust patterns, in early bright stars, in primordial black holes, in something else entirely. What the conversation tells us is that no idea is too old to revisit when the data refuses to fit. Take Gupta's framework at face value, briefly, and ask what it would mean if the universe really were 26 or 27 billion years old, roughly twice the standard estimate. The implications are not subtle. The first thing that changes is the timeline of structure formation. Galaxies need time to assemble. They start as dense regions of dark matter, attracting gas, igniting stars, merging with neighbors. The standard model gives them about 13.8 billion years to do this work. Webb shows mature galaxies appearing within the first few 100 million years, which strains the standard timeline severely. Double the age, and the strain disappears. The mature galaxies become straightforward. They had 13 billion years to grow before the moment we see them. They look mature because they are. The second thing that changes is the role of dark matter. In the standard model, dark matter is the invisible scaffolding that pulls ordinary matter together. Without it, galaxies would not form as fast as they do. The expansion of space would tear gas clouds apart before they could collapse into stars. Dark matter provides the gravitational glue. Gupta's older universe scenario, paired with the covariant constants idea, claims to reproduce galaxy formation without invoking dark matter at all. The slower evolving universe, with subtly different physical constants, accomplishes what dark matter does in the standard picture. Whether the math actually works at every scale is hotly contested. The claim is striking enough to draw attention. If true, dark matter would join the lengthy list of theoretical ingredients that turned out to be artifacts of an incomplete model. Phlogiston, the substance once thought to make things burn, the luminiferous ether, the medium once thought to carry light through space. Each was eliminated by deeper theories. Dark matter could be next. That is a big if. Most evidence still points to dark matter as a real ingredient. Direct detection experiments deep underground have not yet found it, but the gravitational signatures are everywhere. Galaxy rotation curves, gravitational lensing, the cosmic microwave background. Each of these provides independent support for something invisible, holding mass together. Gupta's framework would need to explain all of those signatures without dark matter. Critics argue it cannot. Supporters argue it can. The math is dense, the arguments long, and most working cosmologists are not yet convinced. The third thing that changes is the future. If the universe is much older than thought, then the standard predictions about its long-term evolution may also be off. Heat death, the eventual cooling of all matter and energy into a uniform low-temperature state, might happen on a different timescale. The late acceleration phase of expansion might behave differently. These are speculative consequences. Most of them depend on how the framework is detailed, but even taking Gupta's ideas as a thought experiment is useful. It forces a question that mainstream cosmology has not been forced to ask in a long time. What would it mean if the basic age of the universe is wrong? What would have to change? What would survive? The answer is that almost everything would need to be checked. The age is not a peripheral parameter. It is woven into the calculations behind nearly every cosmic measurement. Change it, and a chain of consequences ripples outward. Most cosmologists are not ready to make that change. The standard age of 13.8 billion years has survived an enormous range of tests. The cosmic microwave background, in particular, gives a precise measurement that aligns with that figure when paired with the standard model. But the mature early galaxies whisper a different number. Webb has heard the whisper. Whether the whisper grows or fades is the question of the next decade. Gupta is not the only scientist proposing that dark matter might not exist. The idea has a small but persistent following going back to the 1980s when Mordechai Milgrom proposed a theory called modified Newtonian dynamics, often shortened to MOND. The premise is that gravity behaves differently at very low accelerations, in ways that mimic the effects of dark matter without requiring an invisible substance. MOND has had partial successes. It explains certain galaxy rotation curves remarkably well, often better than dark matter models with adjustable parameters. It also has notable failures, particularly at the scales of galaxy clusters, where the effects predicted by MONDI fall short of what gravitational lensing reveals. The dark matter alternative landscape is crowded. Modifications to gravity, tired light theories, covariant constants models, each carries its own arguments and critics. What unites them is a shared discomfort with the standard cosmological model. The standard story says that ordinary atoms make up about 5% of the universe. Dark matter makes up about 27%. Dark energy makes up about 68%. So 95% of the universe is invisible to our instruments and unknown to our theories. That ratio bothers some scientists. A theory in which most of the cosmos is mysterious feels suspect. Maybe the mysteries are signs of a broken framework, not signs of new physics. The dark matter detection effort has been running for more than 30 years. Underground experiments shielded from cosmic rays watch for tiny interactions between dark matter particles and ordinary atoms. Particle accelerators search for new species that might match dark matter candidates. Telescopes look for indirect signs of dark matter annihilating into detectable radiation. So far, no direct detection has succeeded. The leading candidate, called the weakly interacting massive particle, has been progressively ruled out across an enormous range of possible masses and interaction strengths. New candidates continue to be proposed, each requiring more sensitive experiments to test. The persistent absence of detection has led some researchers to wonder whether the candidate has been wrong all along. Perhaps dark matter does not consist of new particles at all. Perhaps it consists of primordial black holes, which would not produce the kind of signal direct detection experiments are tuned to find. This is where the early Webb black holes intersect with the dark matter problem. If primordial black holes exist in significant numbers, they could account for some or all of dark matter. They would also explain the rapid growth of supermassive black holes seen by Webb. Two mysteries, one answer. The math has been worked out by several teams. A paper, led by researchers including Yifu Kai and others, examined whether primordial black holes could simultaneously serve as dark matter and as seeds for early galaxies. Their conclusion was that some mass ranges work for both purposes, others fail. The question remains open. The Webb observations of compact, bright objects in the early universe have given primordial black hole models new life. Combined with the absence of direct detection of particle dark matter, the case for an alternative explanation has grown stronger over the past few years. Whether dark matter is a particle, a black hole, or a ghost of broken physics is one of the most consequential open questions in cosmology. The answer will determine the shape of physics for generations. For now, dark matter remains the official answer. Its competitors remain at the edges. Webb has shifted some of those edges closer to the center. When the first stars formed in the early universe, they did not form alone. They formed in groups, gathered along structures that the standard model describes as a cosmic web. Strands of dark matter weaving through space, attracting gas. The web shapes everything that follows. Galaxies grow at the intersections. Clusters form where the strands cross. Voids open in the spaces between. In standard cold dark matter theory, the web is clumpy. Dark matter behaves like a gas of slow-moving particles. They cluster gravitationally into knots and filaments at all scales. Small clumps form first. They merge into larger ones. The hierarchy builds upward. This picture predicts certain shapes for the earliest galaxies. They should be small, roughly spherical, dim, They should grow over time by merging with neighbors, eventually forming the disks and spirals we see today. Webb has shown something different. A paper led by Alvaro Pozo at the Donostia International Physics Center, with collaborators from Arizona State University, MIT, and Harvard, examined the shapes of young galaxies in Webb images. They found that many of the earliest galaxies appear strikingly elongated, not spherical, not disc-shaped, stretched, prolate, like cigars or footballs rather than balls or pancakes. The team ran simulations to see what kind of dark matter would produce such shapes. 3 models were tested: cold, dark matter, the standard scenario; warm, dark matter, in which the particles move faster and smear out small structures; wave dark matter, in which dark matter consists of ultralight particles that exhibit quantum behavior on cosmic scales. The cold dark matter simulations failed to produce the elongated galaxies in significant numbers. The warm and wave simulations succeeded. Their cosmic webs were smoother, less clumpy, more like long, gentle filaments. Gas flowing along these filaments naturally formed elongated young galaxies. The implication is that dark matter might not be the slow, clumpy particle the standard model assumes. It might be something lighter, wave-like, quantum at large scales. Rogier Windhorst, a Regents professor at Arizona State University and an interdisciplinary scientist for Webb, summarized the finding. He noted that in the standard expanding universe, galaxies grow over time from small clumps of dark matter that form the first star clusters and assemble into larger galaxies via collective gravity. But Webb suggests that the earliest galaxies may be embedded in marked filamentary structures, more akin to what is expected if dark matter is an ultralight particle that also shows quantum behavior. That is a significant statement. It does not say cold dark matter is wrong. It says Webb's observations are more consistent with a different kind of dark matter. Ultralight dark matter has been proposed for years. Sometimes called fuzzy dark matter, the particles would be incredibly light, with masses many orders of magnitude smaller than standard candidates. Their wavelengths would be enormous, allowing them to behave like waves on the scales of dwarf galaxies and small structures. Detection has been elusive. Such ultralight particles do not interact strongly with ordinary matter, making them invisible to direct detection experiments. The main evidence has been indirect, looking at the way galaxies form and evolve. Webb has provided new indirect evidence. The shapes of early galaxies do not match the predictions of cold, dark matter. They match the predictions of warmer or wavier alternatives. The cold, dark matter community is not surrendering. There are reasonable rescues. Maybe early galaxy shapes are biased by selection effects. Maybe the simulations need refinement. Maybe small adjustments to the standard picture can reproduce the elongated shapes. But the evidence keeps piling up. Cold dark matter has had a long, successful run. Its first serious challenger in years is wave dark matter, and Webb has just handed it a piece of supporting data. Picture what an early galaxy is supposed to look like. The textbooks show small, roughly spherical clouds of gas and stars, gradually accumulating mass through mergers. By 1 billion years after the Big Bang, you might expect something disc-shaped to begin emerging. By 2 billion years, recognizable spirals. What Webb has shown, in many cases, is something else: cigars, footballs, stretched, elongated objects that look more like compressed lines of light than balls of stars. The shapes are striking. In the Pozo paper and related research, the elongated galaxies appear in significant numbers in the early universe. They are not rare exceptions. They are part of the dominant population at certain cosmic epochs. The standard cold dark matter model has trouble producing these shapes in the right quantities. Cold dark matter forms a clumpy cosmic web. Galaxies forming inside clumps tend toward roundness, not elongation. To stretch a galaxy, you need a smooth flow of gas along a long, narrow channel. Cold, dark matter does not provide that channel reliably. Warm dark matter does. So does wave dark matter. Both create smoother filaments in their cosmic webs. with longer, coherent structures. Gas falling along these structures gets pulled into elongated shapes as it forms stars. The result is the football-like galaxies that Webb sees. The connection between dark matter properties and galaxy shapes is not new in cosmology. Researchers have known for years that different dark matter models predict different patterns of galaxy formation. The challenge was always observing those patterns clearly enough to distinguish between models. Older telescopes could not resolve early galaxy shapes well enough. The data was suggestive but not decisive. Webb changed that. With its sharp infrared eyes, the telescope can resolve the morphology of galaxies as they appeared just 1 billion years or less after the Big Bang. The shapes are no longer fuzzy blobs. They are detailed objects with measurable axis ratios and orientations. The POSO team examined 6 representative galaxies in their analysis. The top row of their figures showed Webb images of marked filamentary galaxies. The middle row showed warm dark matter simulations of galaxies that closely resembled the observations. The bottom row showed cold dark matter simulations of the same systems. The cold dark matter simulations did not look like the Webb images. The warm dark matter simulations did. The visual comparison was clear enough to convince several researchers that something needs to change in the standard model. Not necessarily a wholesale replacement of cold dark matter, but at least a careful reconsideration of which version of dark matter is most consistent with high redshift observations. The implications stretch beyond galaxy shapes. If dark matter is warmer or more wave-like than the standard model assumes, then the small-scale structure of the universe would also be different. There would be fewer tiny dwarf galaxies. The cores of galaxies would be smoother. The rotation curves of small galaxies would behave differently. Some of these predictions can be tested. Surveys of dwarf galaxies in the local universe are looking for the missing satellites that warm or wave dark matter would predict. The matchup is ongoing. Some observations support warmer models. Others support cold dark matter. The picture is not yet settled. Webb has put a thumb on the warm dark matter side of the scale. If dark matter turns out to be ultralight, with wave-like quantum behavior on cosmic scales, the consequences ripple through almost every part of physics. The standard candidate for dark matter, the weakly interacting massive particle, would weigh perhaps 100 times the mass of a proton. Ultralight dark matter, by contrast, could weigh 100 trillion times less. The numbers are nearly impossible to picture. Such low-mass particles would have extremely long quantum wavelengths. On the scales of galaxies, the wavelengths could be measured in light years. The dark matter would not behave like a collection of point particles. It would behave like a continuous wave, oscillating gently across enormous distances. This changes how dark matter clumps. Cold dark matter forms tight, dense halos. Wave dark matter forms looser, fuzzier halos with smooth cores. Galaxies sitting inside wave dark matter halos would look slightly different. The centers would be less concentrated. The outer regions would be smoother. Some observations support this. Dwarf galaxies in the local universe sometimes show flat density profiles in their cores rather than the steep centers. Cold dark matter predicts. This is called the core cusp problem. Cold dark matter says cusp. Observation says core. Wave dark matter naturally produces cores. Other observations push back. The cosmic microwave background, the early universe relic radiation, places tight constraints on dark matter properties. Wave dark matter has to be carefully tuned to avoid contradicting CMB measurements. Some versions survive, others do not. The detection challenge is severe. Ultralight particles do not bounce off atoms. They do not produce visible radiation. They interact almost exclusively through gravity. The main experimental approach has been to look for their wave-like effects on precision instruments. Atomic clocks, for instance, might tick at slightly different rates if surrounded by oscillating dark matter waves. So far, no detection has succeeded. The constraints on wave dark matter come almost entirely from astronomy. Galaxy shapes, galaxy clustering, the cosmic web. Webb has added a new line of evidence. The early elongated galaxies and their filamentary surroundings are easier to explain with wave dark matter than with the standard cold version. If wave dark matter wins, physics changes. The weakly interacting massive particle becomes a discarded hypothesis. Direct detection experiments running for decades become historical artifacts. New searches, focused on wave-like signatures, become the priority. Quantum effects on cosmic scales become a real subject of study, not a theoretical curiosity. The change would not undo Einstein's general relativity. It would not eliminate the Big Bang. It would, however, rewrite a substantial chunk of the picture between those two pillars. The matter, content of the universe, the way structure formed, the behavior of galaxy halos, all of it would shift. Most cosmologists are not yet ready for that shift. The case for cold dark matter is built on decades of evidence, much of it consistent with the standard particle picture. Replacing it requires more than one suggestive observation, but the suggestive observations are accumulating. Webb has provided several. The elongated early galaxies are one. The hints of unusual galaxy core densities are another. The persistent failure to detect heavy dark matter particles is a third. Add them together, and the case for wave dark matter has grown from speculation to serious hypothesis. The conventional wisdom on black holes is that they form from dying stars. A massive star runs out of fuel, collapses under its own gravity, and forms a black hole. Repeat the process across billions of years, and you get the population of stellar mass black holes scattered through galaxies today. For supermassive black holes, the story is more complicated. They are millions to billions of times the mass of the Sunday stars cannot directly produce them. Instead, smaller seed black holes are thought to grow over cosmic time by feeding on gas and merging with each other. The process should take a long time, hundreds of millions of years at minimum. Webb has shown that supermassive black holes existed at times when this process should not have been complete. Galaxies, just a few 100 million years after the Big Bang, already host black holes weighing millions of solar masses. The standard story does not have time to make them. The escape route the Webb data points toward is an old one: primordial black holes. Black holes that did not form from collapsing stars at all. Black holes that formed in the chaos of the first second after the Big Bang. The original proposal goes back to Yakov Zeldovich in 1966 and Stephen Hawking in 1971. They noted that the early universe was not perfectly uniform. Tiny variations in density existed. If a region happened to be overdense by a sufficient amount, it could collapse directly into a black hole without needing stars. The masses of primordial black holes could span an enormous range. Tiny ones might weigh as little as a millionth of a gram, evaporating quickly through Hawking radiation. Larger ones might persist to the present day, hidden among ordinary matter. The biggest could weigh thousands or even millions of solar masses, ready to seed the first galaxies. For decades, primordial black holes remained a fringe idea. Direct evidence was lacking. The standard picture of stellar collapse seemed sufficient to account for known black holes. Why complicate things with a hypothetical population from the early universe? Webb has changed the calculation. The early supermassive black holes need an explanation. Primordial black holes are one of the cleanest available. A paper by Zhiqiang Shen and colleagues at the Hong Kong University of Science and Technology proposed that primordial black holes with masses of around 1,000 solar masses could serve as seeds for the early galaxies seen by Webb. Their Bayesian analysis preferred a log-normal mass distribution centered around 750 solar masses. Drop these primordial seeds into dense gas clouds in dark matter halos. Allow them to feed at super Eddington rates for short periods. Let them merge with each other. Within a few 100 million years, they grow into the supermassive black holes Webb observes. The math fits. The framework provides explanations for both the early galaxies and the early supermassive black holes simultaneously. Other researchers, including A.D. Dolgov at Novosibirsk State University, have argued similar lines for years. Dolgov, building on earlier work with Joseph Silk from the 1990s, has argued that supermassive primordial black holes could naturally seed galaxy and quasar formation in the very young universe. The Webb observations have brought renewed attention to this old conjecture. If primordial black holes are real, they could solve multiple puzzles at once. The early supermassive black holes get seeds. The early bright galaxies get extra energy sources. Possibly, dark matter gets a candidate. The unified picture is appealing. The challenge is detection. Primordial black holes interact mostly through gravity. They do not emit light unless they are actively feeding. They do not show up in particle detectors. The main evidence is indirect, through their gravitational effects on other matter. Webb is, in a sense, the first instrument capable of seeing the indirect evidence at the right cosmic time. In the early 1990s, A. D. Dolgov and Joseph Silk wrote a paper proposing that primordial black holes could form with a particular mass distribution called log normal. The idea was technical, the audience small, and the prediction lay quietly in the literature for 30 years. Most theoretical predictions in cosmology never get tested in their authors' lifetimes. The cosmos is large, the relevant times are remote, and the technology to make the necessary observations often takes decades to develop. Dolgov and Silk's prediction was different. It got tested. By Webb, the log-normal mass distribution they proposed for primordial black holes turned out to match the masses needed to seed early supermassive black holes. The prediction made in the early 1990s by physicists who could not have known what Webb would find fit the data Webb produced 30 years later. That kind of match is the gold standard of theoretical cosmology, a specific prediction made before the data exists that turns out to align with the eventual observation. It does not prove the theory correct, but it raises the prior probability significantly. Dolgov, in his more recent papers, has not been shy about claiming credit for the alignment. He has written that the 30-year-old conjecture not only rescued the standard cosmological model, but in fact predicted the observed rich population of the early universe, with developed galaxies and quasars. That phrasing is partly hyperbole, partly genuine pride. The full match between the theoretical prediction and the Webb data is not perfect. Adjustments are needed. Other cosmologists dispute aspects of the analysis, but the basic shape of the prediction holds up surprisingly well. The mechanism Dolgov proposes for primordial black hole formation is itself unusual. It does not involve simple density fluctuations collapsing into holes. It involves a complex dance between matter and antimatter in the very early universe, leading to overdense regions that selectively collapse. The details are technical. The result is a population of black holes with specific masses, ready to seed structure formation. The paper has been cited heavily in the post-Webb era. Researchers around the world are running new simulations to test whether the proposal fits the full set of Webb observations. Some find good matches, others find tensions. The verdict is not yet in. What is clear is that primordial black holes have moved from a fringe idea to a mainstream consideration. The Webb observations have given them a platform that decades of theoretical work could not. If primordial black holes are eventually confirmed as the seeds of early galaxies, the implications go beyond cosmology. The formation of these objects in the first second after the Big Bang would tell us something profound about the conditions of that era, the energies, the fields, the quantum fluctuations that shaped the early universe. Some of the questions about the moment of cosmic birth might find answers in the masses and distributions of primordial black holes. The objects themselves would be fossils, carrying information about an epoch we cannot otherwise probe. For now, the case is suggestive but not conclusive. The Webb data fits primordial black hole models well. It also fits other models, with varying degrees of success. The next generation of telescopes, including the Roman Space Telescope and various ground-based facilities, will help distinguish between explanations. Dolgov is in his 80s. He may live to see his 30-year-old prediction confirmed or disproved. Many theorists never get that chance. Webb has accelerated the timeline. Black holes do not eat instantly. They have a speed limit. Material falling toward a black hole heats up and radiates energy. The radiation pushes back against the inflowing matter. At a certain rate of accretion, the outward radiation pressure balances the inward gravitational pull. The black hole cannot grow any faster. This balance point is called the Eddington limit, after the British astrophysicist Arthur Eddington, who derived it in the early 20th century. For a typical supermassive black hole, the Eddington limit allows growth on a characteristic timescale of about 50 million years. Doubling the mass takes that long. To go from 1,000 solar masses to 1,000,000 takes many doublings, which adds up to several 100 million years at the limit. The Webb observations show black holes that have grown faster than this. They appear too massive, too soon. Either the Eddington limit can be broken, or the seeds were already large. Both possibilities are being explored. Super Eddington accretion, breaking the limit, has been observed in some local sources. Black holes can apparently exceed the limit for short bursts when the geometry of the inflowing matter allows the radiation to escape sideways without slowing the accretion stream. Whether this can be sustained for the durations needed to grow early supermassive black holes is debated. The alternative is heavy seeds. Start with a black hole already weighing tens of thousands or even hundreds of thousands of solar masses. Then growing to 1,000,000 in a few 100 million years requires only modest accretion. The Eddington limit becomes a comfortable speed, not a barrier. Heavy seeds can come from two sources: direct collapse of huge gas clouds in the early universe, where the cloud bypasses the star formation phase entirely and collapses straight into a massive black hole, or primordial black holes formed in the first moments after the Big Bang. The primordial route is gaining favor in many recent papers. The direct collapse route is also viable, but requires specific conditions that may have been rare. The choice between the two has consequences for what kind of dark matter is preferred and how the early universe behaved. Either way, the Webb black holes need an explanation. Standard star collapse seeds growing at the Eddington limit do not have time. Something has to give. The little red dots, with their possible black hole star nature, fit naturally into this picture. Whatever they are connected to the early growth of supermassive black holes. They appeared at the right time. They had the right luminosities. They disappeared when the black hole growth phase wound down. The timing is suggestive. Some researchers have proposed that the little red dots are the visible signatures of super Eddington accretion onto heavy seed black holes. The dense gas clouds surrounding the growing black holes absorb most of the X-rays, preventing detection by Chandra, while emitting in the infrared as Webb sees them. This unified picture, with primordial or direct collapse seeds growing at super Eddington rates inside little red dot clouds, accounts for many of the strangest features of the early universe. It is not yet the consensus view. It is gaining ground. The cosmos that Webb is showing us seems to have built its first supermassive black holes through processes that the standard model did not anticipate. The objects are real, the masses are large, the timescales are short. Some combination of unusual seeds and unusual feeding has to be invoked. Each new Webb observation tightens the constraints. The picture is becoming clearer. The picture is also becoming stranger. When the rotation asymmetry was first reported, an obvious objection appeared. Maybe it is not real. Maybe the apparent excess of clockwise galaxies is an artifact of our own motion through space. The argument goes like this. The Earth orbits the Sunday. The Sun orbits the center of the Milky Way. The Milky Way moves through the local group of galaxies, which moves through the Virgo supercluster, which moves through still larger structures. We are not stationary. We are flying through space at hundreds of kilometers per second. This motion has consequences. Light from objects we are moving toward gets blue shifted. Light from objects we are moving away from gets red shifted. The brightness can also change slightly. Objects we are approaching look slightly brighter. Objects we are receding from look slightly dimmer. Apply this to galaxy rotation. A spiral galaxy spinning counterclockwise relative to the Milky Way has parts of its disk approaching us and parts receding from us. The approaching side looks brighter. A galaxy spinning clockwise has the same effect, just with the brighter side reversed. If our motion happens to favor one configuration over the other, we might see more galaxies of one rotational sense simply because the brighter ones are easier to detect. Lior Shamir himself acknowledged this possibility in his paper. He noted that if the Doppler explanation holds, then we would need to recalibrate distance measurements for the deep universe. The recalibration could explain other unsolved questions in cosmology, such as the differences in the expansion rates of the universe and the large galaxies that, according to existing distance measurements, are expected to be older than the universe itself. That sentence carries a lot. If the rotation asymmetry is a Doppler artifact, it might also explain the Hubble tension. It might also explain the apparent mature galaxies that look too old. A single observational bias, traced back to the motion of our home galaxy, could be sitting at the root of multiple cosmic puzzles. That would be remarkable. Not a new physics result, a measurement correction. The cosmos would be normal. Our calibration would be off. But the Doppler explanation requires the Milky Way's rotation to have a non-negligible impact on our observations of distant galaxies. Standard estimates of the Milky Way's rotation speed suggest the impact should be small, too small, in fact, to produce the level of asymmetry Shamir reports. If the asymmetry is real and Doppler-caused, then either the Milky Way is rotating faster than we thought, or our calibrations have systematic errors, or some combination of effects. None of these is a small adjustment. The Doppler defense is the most boring possible explanation for the rotation asymmetry. It is also the explanation that would have the largest practical consequences for everyday cosmology. Rewriting distance measurements would touch every survey, every redshift estimate, every mass calculation that relies on cosmic distance ladders. The alternative, that the universe really has a preferred axis, baked in from creation, is more exciting but less well constrained. It would require accepting that the universe was born rotating, possibly inside a parent black hole, and that the rotation imprinted itself on galaxy formation. Shamir does not pretend to know which explanation is correct. He presents both possibilities and lets the data decide. Future observations, with larger samples and more diverse fields, will tell us whether the asymmetry is real or whether it dissolves under closer inspection. For now, the rotation finding remains genuinely uncertain. Both interpretations have implications. Both would change cosmology. If the Doppler explanation for the rotation asymmetry is correct, then the Milky Way's spin is not the small effect that standard estimates suggest. It must be larger, significant enough to bias our view of the entire deep universe. Most astronomers have treated the Milky Way's rotation as a known quantity. The Sun orbits the galactic center at roughly 230 kilometers per second. The orbital period is about 230 million years. We have made one full circuit since the early dinosaurs walked the Earth. These numbers are based on detailed observations of nearby stars and gas. They are not perfect, but they are well constrained by multiple independent methods. Yet Shamir's analysis suggests that the impact of this rotation on our deep space observations might have been underestimated. If the asymmetry he detects is purely Doppler-caused, then the Milky Way's contribution to the apparent brightness of distant galaxies is larger than mainstream estimates allow. This is uncomfortable. It would mean that decades of cosmic distance measurements have a bias none of us noticed. A small but persistent error, traceable to our home galaxy, threading through the published numbers for galaxy distances, masses, and ages. The implications spread quickly. Mass estimates of distant galaxies depend on accurate distances. If those distances are wrong, the masses are wrong. The famously massive early galaxies seen by Webb might be less massive than reported. The apparent paradox of mature galaxies in the early universe might soften. The Hubble tension might also be affected. The expansion rate measured locally depends on a chain of distance calibrations. If the chain has a hidden Doppler-related bias, the local rate could be wrong by exactly the percentage needed to bring it into agreement with the early universe rate. That would be an extraordinary outcome. A single hidden bias resolving multiple puzzles simultaneously. No new physics, no exotic dark matter, no primordial black holes required. This scenario has a dramatic appeal, the simplest possible explanation for several cosmic mysteries. Our calibration, our blind spot, our error. It also has a difficulty. The bias would need to be quite specific. It would need to affect distance measurements in just the right way to resolve the Hubble tension while also producing the observed galaxy rotation asymmetry. It would need to leave the cosmic microwave background measurements alone. It would need to fit the supernova data, the galaxy clustering data, and the gravitational lensing data without contradiction. Designing a Doppler correction that does all of this without breaking something else is not easy. Some researchers think it is possible. Others think the Doppler explanation is a red herring, a tempting simplicity that does not survive detailed analysis. The truth, as usual, will require more data, larger samples of galaxy rotations, surveys covering multiple regions of sky, independent tests of the Milky Way's true rotational influence on deep space observations. A study by Shamir himself in 2025, building on earlier work, concluded that astronomers should factor the Milky Way's rotational velocity into observations of deep space galaxies. The recommendation is straightforward. Whatever the correct interpretation, the effect is large enough that it should not be ignored. Whether the rotation asymmetry is a sign of cosmic anomaly or a sign of observational bias, it is teaching us something important. We are not as steady an observation platform as we thought. Our home galaxy moves. That motion matters. Take stock of where the modern cosmology stands. The Webb observations have not produced a single contradiction with the standard model. They have produced several. Some of them might be related. Most of them might not be. The mature early galaxies do not fit the standard timeline of structure formation. The supermassive black holes appear too soon for standard seeding mechanisms. The rotation asymmetry hints at a preferred cosmic axis. The Hubble tension persists despite multiple independent confirmations of measurement accuracy. The little red dots represent a population of objects with no clear analog in older theories. The elongated early galaxies suggest dark matter might not behave as the standard model assumes. The galaxies appearing older than the universe itself raise the possibility that the cosmic age is wrong. Each of these is a crack. Each one alone could be patched with careful additions to the existing framework. Together, they suggest that the framework itself might be straining. What might cause all of these cracks at once? Several possibilities exist. None is universally accepted. Each has supporters and critics. One possibility is that the standard model is fundamentally correct, but is missing several auxiliary ingredients: early dark energy, primordial black holes, modifications to dark matter properties. Added together, these might patch the various cracks while leaving the core framework intact. Another possibility is that one of the model's foundational assumptions is wrong. Perhaps the cosmological principle, the assumption that the universe is the same in every direction, is mistaken. The rotation asymmetry would naturally fit. The Hubble tension might fit too, if local rates differ from global rates. A third possibility is that gravity itself behaves differently at large scales than general relativity predicts. Modified gravity theories have a long history. Most have failed. Some persist. The Webb data has given new life to several proposals. A fourth possibility, the most dramatic, is that the universe is not what we have been calling it. The black hole cosmology theory, the older universe scenarios, the alternative dark matter models, all of these would represent a substantial rewriting of the cosmic story. Most cosmologists are not yet ready for the dramatic options. The standard model has survived a long stretch of testing. Replacing it requires more than suggestive observations, but the suggestive observations are accumulating fast. Each new Webb image, each new survey, each new analysis adds another data point. The cracks are not closing, they are widening. A senior cosmologist, asked about the state of the field, used a phrase that captures the moment well. He said, "Cosmology is in a renaissance, not a crisis." Exactly, because crisis implies something is broken beyond repair. Renaissance implies a period of intense rebuilding, where old certainties give way to new ideas, and the boundaries of what is possible expand. The Renaissance has been underway for a few years now. Its driver is Webb. The telescope has provided data that no previous instrument could match. The data has revealed gaps in our theories. What comes next is the construction of new theories that fill those gaps. Some will succeed, most will fail. The eventual winner might be a refined version of the standard model, with additional ingredients. It might be something far stranger, the galaxies older than the universe, the spinning patterns, the impossible black holes, the missing red dots. All of them are clues. The puzzle they assemble has not been solved. The pieces are still being laid out. What can be said is that the universe is more complicated than the standard model predicted. The simplest version of the cosmic story is not quite right. The real story has surprises that nobody anticipated. General relativity is now more than 110 years old. Einstein published the theory in 1915. In the decades since, it has passed every test thrown at it. The bending of starlight by the Sunday, the orbit of Mercury, the gravitational redshift of light, the slowing of clocks in gravitational fields, gravitational waves from colliding black holes. Each test has confirmed the theory to extraordinary precision. Yet general relativity also predicts its own breakdown. At the centers of black holes, the equations produce singularities, points of infinite density where the math no longer makes sense. At the moment of the Big Bang, the equations again break down. These are not flaws of the theory. They are signposts saying that beyond this point, something deeper must take over. Quantum mechanics, the other great pillar of modern physics, is also more than a century old. Its predictions match experiments with absurd accuracy. Yet quantum mechanics and general relativity have never been fully unified. At the smallest scales, where quantum effects should dominate even in gravitational settings, the two theories give incompatible predictions. The search for quantum gravity has consumed generations of theorists. String theory and loop quantum gravity are the leading candidates for a unified framework. Neither has produced clear experimental predictions yet. Both make claims about the universe at scales far smaller than current instruments can probe. Webb does not directly test quantum gravity, but its observations of the early universe, the regime where quantum gravity should matter most, push the boundaries of our framework. The patterns Webb sees are sensitive to conditions in the very early cosmos. Those conditions, if traced back far enough, lead to the quantum gravity regime. The mature early galaxies, the rotation asymmetry, the early supermassive black holes, all of these depend on the conditions of the early universe. Slight modifications to general relativity or to quantum mechanics in those conditions could produce different outcomes. The Webb observations might be probing the boundary of where our current frameworks apply. Some theorists are already exploring modified gravity scenarios that affect early universe cosmology. Others are looking at quantum effects on cosmic scales. Each proposal makes specific predictions for what Webb should see. The matchup is being checked. So far, no single modified theory has emerged as the winner. The standard combination of general relativity plus the standard model of cosmology continues to provide the best overall fit, though with the various tensions noted in earlier chapters. What the Webb data has done is open the door to alternative frameworks. The standard model is not the only game in town. Modified gravity, quantum cosmology, black hole cosmology, ultralight dark matter, primordial black holes, all of these now have a seat at the table. They were always theoretical possibilities. Now they have observations that might support them. Einstein's framework will probably survive. It has too much predictive power to be overthrown lightly. What might change is its application at the largest scales and the earliest times. The framework might need extensions, modifications, additional ingredients. The pattern of how physics evolves is well known. Newton's mechanics worked beautifully for everyday objects. It was extended, not replaced, by Einstein at high speeds and strong gravity. Einstein's gravity might in turn be extended, not replaced, by some future framework that handles the cosmic boundaries better. Webb might be helping us identify where those extensions need to go. The view from Earth's perspective is humbling. The framework that has guided physics for over a century is encountering observations that strain its limits. The strain is not yet a break. It is a signal, a request for refinement. Somewhere, in the equations or in the cosmos, an answer is waiting. Webb has helped us see the question more clearly than we ever could before. Imagine, briefly, that all the strangest interpretations turn out to be correct. The universe was born inside a rotating black hole in some larger parent cosmos. Its rotation imprinted itself on galaxy formation, producing the observed asymmetry. Primordial black holes formed in the first second after the Big Bang, seeding both dark matter and the first galaxies. Dark matter is ultralight and wave-like, producing smooth filaments rather than clumpy halos. The Hubble tension is real and points to new physics in the form of evolving dark energy. If all of this is true, the cosmos is not the universe described in standard textbooks. It is a different place. A place with a parent, a place with a rotation, a place built from primordial seeds rather than stellar collapse, a place where the invisible matter is a quantum wave, not a particle. This is not the cosmos most working scientists believe in today. It is one of several possible cosmoses suggested by current data. Whether it turns out to be correct or not, the fact that it can be seriously entertained is itself a major shift. 20 years ago, almost none of these ideas would have been mainstream. They were on the edges of cosmology, defended by small groups of theorists, dismissed by most others. Webb has changed the conversation. The edges have moved closer to the center. The mainstream has expanded to include possibilities it would have ruled out a decade earlier. The implications stretch beyond science. If the universe is one of many, with parent and possibly child universes, the philosophical landscape changes. The question of what is fundamental shifts. Fine-tuning arguments take on new meaning. Anthropic reasoning, the idea that we observe a universe compatible with our existence because no other universe could be observed by us, becomes more concrete. If primordial black holes seed structure and constitute dark matter, the bridge between the very early universe and the present cosmos becomes a single object, a black hole formed in the first second, persisting for 14 billion years, anchoring a galaxy, hosting our understanding of the universe. That is a different kind of cosmic biography. If dark matter is wave-like, the very small and the very large are connected through quantum behavior. The universe is not a collection of point particles. It is a layered structure of waves, with classical objects emerging from quantum substrate at certain scales. This is not new in physics. It is new at cosmic scales. If the rotation is real, the universe inherited a memory. The act of cosmic creation was not erasure. Something persisted. The parent cosmos, whatever it was, left a fingerprint. These possibilities are not certainties. Many of them might fail under closer testing. The next decade of telescopes, including the Roman Space Telescope, the Extremely Large Telescope, and various survey instruments, will sharpen the picture. Some current ideas will be eliminated. Others will be confirmed. New ideas will emerge. What seems clear is that the universe is more complicated, more interconnected, and more strange than standard cosmology suggested. The cosmos does not match a simple recipe. It matches a complex story with multiple plots, some of them unfinished. Webb has been the lens through which the complexity has come into focus. The instrument has served its purpose. It has shown us things we did not expect to see. It has unsettled certainties that needed unsettling. It has prepared the ground for the next generation of discovery. Whatever the eventual answers, the questions are now richer than they were before Webb launched. Stand for a moment at the edge of what we now know. The universe is roughly 13.8 billion years old. By standard counting, it contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. Most galaxies host central supermassive black holes. The whole structure is held together by invisible scaffolding called dark matter. The whole expansion is being driven by an even more mysterious force called dark energy. That is the official picture. It has survived a century of testing. It is also showing cracks. The cracks have names now. The Hubble tension, the mature early galaxies, the little red dots, the rotation asymmetry, the elongated young galaxies, the galaxies older than the universe. Each crack has its own literature. Each has its own proposed solutions. What unites them is a shared origin. They were all opened or sharpened by James Webb. The telescope launched in December of 2021, parked at its observation point 1 million miles from Earth, and began returning images that nobody had quite anticipated. The instrument was designed to study the early universe. It has done that job superbly. It has also done something else. It has shown that the early universe is not what we expected. The differences are not small. They are not within the noise of standard models. They are real, persistent, and growing. Whether the standard model will survive the Webb data with modifications, or whether it will be replaced by something far more radical, is the central question of contemporary cosmology. The answer will not arrive this year. It probably will not arrive this decade. The data is still flowing in. The theoretical work is still progressing. The arguments are still being made. What can be said is that the next chapter of our cosmic understanding is being written now, not in textbooks, in journal papers, conference talks, and late-night arguments between cosmologists. The conversation is dense and technical, but it is moving fast. One of the senior cosmologists involved in the discussions described the moment well. He said the Webb data is like looking at the universe in high definition for the first time. The signal-to-noise of measurements has improved dramatically. Things that were blurry are now sharp. Things that were ambiguous are now definite. That clarity has come at a cost. The clearer view has revealed inconsistencies that older, blurrier views had hidden. The standard model worked well when the data was less precise. With Webb's precision, the seams have started to show. Some of those seams might be sewn back together with careful additions to the theory. Others might require ripping out larger sections and rebuilding. Which seams need which treatment is the question being worked out now. For the rest of us, the takeaway is straightforward. The universe we live in is more interesting than the textbook version. The standard model is not wrong, but it is incomplete. The complete version, when it eventually emerges, will be stranger than what we currently teach. The galaxies are spinning the wrong way. The masses are too large. The expansion rates do not match. The little red dots blink in and out of cosmic time. The dark matter might be a wave. The black holes might be older than the stars. The universe might be sitting inside something larger. Most of these statements would have sounded like science fiction 5 years ago. Today, they are entries in serious cosmological discussions. Webb made the transition possible. What comes next depends on the next generation of telescopes, the next decade of observations, and the next round of theoretical work. It depends on data that has not yet been collected, ideas that have not yet been formulated, surprises that have not yet been encountered. If the past few years are any guide, the surprises will keep coming. The universe is bigger, weirder, and more honest than we knew. Webb has shown us a cosmos that does not fit our maps. The maps are being redrawn. The cosmos is patient. It has held its secrets for billions of years. It is starting, finally, to share them.